let me recall the very last thing we were doing last time. So with a little bit more notation, so let me introduce some more facts, some more notation. So if I have lambda in P plus, so which is a dominant integral weight, what we were trying to answer is the following question. Let's take the straight line path from 0 to lambda, we call this pi lambda, and we wanted to understand what sorts of paths do you get when you act Fi's on this guy. Okay, so let me give that set a name. So I'll call it B of lambda. This is just by definition the set of all paths obtained by repeated actions of Fi's on it. Okay, where the Fi's are, let me not, all possible Fi's. So all sequences, varying over all possible sequences of Fi's. Okay, so this collection of paths, we wanted to understand what sorts of things can arise in this manner. And one thing we said is that the directions in which the path travels, at least that bit is known, meaning that's quite easy to describe, which is that it travels along various Weil conjugates of lambda. So what we said is any path in B lambda is necessarily of the following kind. So I'll call this paths of class lambda. So by paths of class lambda, so I'll just say paths lambda. I'll just mean all paths whose the directions of travel are some Weil conjugates of lambda. Okay, so paths of lambda will just mean all paths of the following form. So let me not be too formal about it. Let me draw the paths. You start at the origin, then each segment. So it's some new one until time t equals a1. So this is a time stamp. So at time t equals a2. So this is new 2, then new 3. And so on. So at each time I change direction, travel along these guys where all the new i's are Weil conjugates of lambda. So that's the condition here. Okay, so it's given by two pieces of data, new 1, new 2, new r, and a1, a2, ar, the timestamps and the directions. Okay, so such things we'll call paths of class lambda. So one thing we have noticed is that definitely anything in B lambda must be in paths of lambda. Right? If we apply Fi's, the directions of travel are necessarily some Weil conjugates of lambda. So that's the easy observation we made. Now the thing we were starting to do last time was to get more conditions. So we eventually want to try and characterize B lambda, get enough conditions on such paths so that the set of paths you get are exactly the paths of B lambda. Okay, so the first thing is that, so before I go back to that partial order that we introduced last time on the Weil group and so on. So okay, so maybe I'll just say that quickly, and we'll come back to this. So that we introduced a partial order on the Weil orbit of lambda, and if you remember the picture yesterday from 2 epsilon 1 plus epsilon 2 being lambda, so there's sort of a hexagon. So this was you can draw it in many different ways. So let me say this is the hexagon, and then so this was the partial order. Okay, there were 6 Weil conjugates, and then this is the largest element, and you sort of, these arrows tell you which is greater. So this is greater than this, is greater than this, and so on, right? And we had a formal definition for this partial order. It was that each line in this diagram represents a pair of Weil conjugates which are obtainable one from the other by a reflection, and the arrow tells you which of these two guys is bigger than the other, in the sense of their difference should lie in the positive part of the root lattice. Okay, so that was the definition of the partial order. And so let's see how this partial order sort of arises naturally when we try to answer this question, when you try and find out what B lambda is. Okay, so to do this, let's look at paths of lambda which are sort of one segment paths. So let me first start out by considering some examples of paths. Suppose I have one segment paths of class lambda. Okay. So what is a one segment path of class lambda? By definition, it just has one segment, which means there's only one travel direction. So I start at the origin, I travel along some nu 1, or let's call it nu here, where nu is, so this is the travel direction, and I have to travel for time 1, t equals 1, because there are no further changes of direction. So this endpoint therefore is also a nu. Okay, my travel direction is nu, my endpoint is also nu. Correct? So I travel along the direction nu for time 1. Now this, where what's nu? Nu must be some Weil conjugate of lambda. Okay. Now if I take any path of this kind, so the first question is such a path in B lambda? Can a one segment path be obtained as, obtained by acting a string of f's on the straight line path pi lambda? Okay, so let's ask that question for a start. So maybe to do this, let's take a sort of somewhat simple example. Let's not take a general element here. For a start, let me just say it has, let me take a one segment path of this particular type. Let me just take Si lambda, it's obtained by acting as a single simple reflection. Okay. So if I take this Si lambda, now let's ask, suppose I take this path from the origin to Si lambda, can I get this path by acting by some Fi's on the straight line path pi lambda? Okay. So let's start with the path pi lambda, that's the guy on which we need to start acting. So here's 0, here's lambda, so this is a path pi lambda. So when I act Fi on this guy, so let's try to act Fi, so somehow here there is an I here, so let's hope that Fi is relevant. So in order to act Fi on this path, I need to construct the function hi pi. Okay. Now what does that function hi pi look like? It's just a straight line, because this only has one segment, right? And this ends at lambda. So this is a straight line, and where does it end? The y coordinate will be lambda evaluated on alpha I check. Okay, it's just straight line path going up to that point. Okay. Now from this path I am attempting to obtain this path. So what is this path? It's the path, maybe I shouldn't draw it pointing up the same way. This path here that I am talking about is obtained from that guy by performing a reflection Si. So this is Si lambda, right? This endpoint is Si lambda. But I have to perform a reflection on the entire path. Okay, I have to take the entire thing and reflect it by an Si. Okay. So is that operation obtainable by acting a single Fi? If what is an integer? If lambda alpha I check is 10, how? If I act a single Fi on that path. If I act it, why? Right, okay. So we have sort of seen this, right? If you act multiple Fi's, if I want to apply Fi power 10, I have to shine a beam of width 10, and that beam will sort of hit the entire line. Right? Now lambda of alpha I check, by the way, is always an integer, because lambda is an element from the root lattice, from the weight lattice. Okay, it's an element of p plus, it's a dominant thing. So if you remember the definition of what p plus was, this means that it is a non-negative integer always. That's the reason why I sort of drew it on top. And now all you have to do is just shine a light beam of width lambda alpha I check. The entire region gets illuminated. Therefore, the entire region gets reflected. So in other words, I take pi lambda and if I apply the operator Fi, lambda alpha I check times. Okay, if I apply these many times, it will just give me this guy, Si. Okay, so all these things of this kind are definitely in, so one segment paths where this guy is Si lambda certainly is in B lambda, but in fact more generally, so you just have to do this, repeatedly. A typical element of W lambda will look like this. It's not just a single Si acting on lambda, it will be Si1, Si2, Sik acting on lambda. Okay, you have to act many Si's, and now you can do this step by step. So you first get a straight line path which ends at Sik lambda, and now on this you apply a suitable, so this will be Fik those many times. Now on this you have to act Fik minus 1 a suitable number of times, okay, and that will give you the other guy, and so on. Okay, so there's a little work to be done here, maybe it can be done in one of the tutorial exercises, which is from this method of obtaining straight line paths ending at Si lambda, sort of just do it iteratively and figure out how to obtain straight line paths which end at all the other while conjugates. Okay, so this is just a little bit to be done, not too hard. So in other words, what have we shown here? We have shown that all one segment paths in paths of lambda, all one segment paths of class lambda are in fact in B lambda. Okay, so one segment paths are done. Everybody here is there. Okay, so in some sense we need to start understanding what two segment paths look like. So that's our second example. So let's look at two segment paths of class lambda. And now let's ask, does every two segment path belong to B lambda? Can any two segment path of class lambda be obtained as some application of Fi's on pi lambda? Okay, so it will turn out not to be the case. So there are some further conditions that the two segment path will have to satisfy before it can possibly lie in B lambda. So let's do a little bit of heuristics here just to see what sorts of conditions will be necessary. Okay, so I'm not going to do too rigorously, just think of it as heuristics at this point. So what is a two segment path? How do you get a two segment path? Okay, so one way of getting a two segment path is you could start with a one segment path, say which ends at some mu, okay, and then apply an Fi to it. Okay, how do you generate two segment paths, right, in say which are in B lambda? So I'm thinking about how do two segment paths in B lambda look. They are typically going to be, you take some one segment path and maybe you apply an Fi and a certain region gets illuminated and say this region gets reflected, right. So this was the original path. To mu, and a certain portion of the path gets reflected and the rest is the same. Okay, so this is the part of the path which was illuminated and it got reflected by some Fi. So let's say I acted an Fi on a one segment path and it became two segment. Okay, so let's say that this path was obtained from this guy by acting an Fi. So is the diagram clear? I mean, what I'm trying to draw, this thing on top is my original path pi, and the thing on the bottom is my new path Fi acting on pi. Okay, pi is one segment, Fi pi is two segment. Okay, now let's look at these. What happened when you moved from pi to Fi pi? This guy had a single direction mu, but this fellow now has two directions. So the second direction is still a mu, and the first direction here is a nu. Okay, so that's a nu. So this is almost like, I mean, imagine your pi lambda, for example. So anyway, so I have a nu and a mu. Now the point is, so I'm saying that I got Fi pi from pi by acting an Fi. Now what does Fi do to the endpoint? So what happened when I moved from this path to this path? The endpoint, it goes Si lambda. No. What does a single Fi do? It's a lowering operator, right? It lowers the endpoint by an alpha I. That's the, so this new endpoint here is alpha I smaller than the original endpoint. So pi, Fi pi, the new path, its endpoint is lower than the original guy by an alpha I. Okay, and that lowering must of course have happened right here. Right, the portion that got reflected there, already an alpha I decrease happened. The rest anyway keeps just comes along for the ride, right? So this, there is a certain decrease by this amount alpha I. Okay, so now, so let's compare the original and the new path. So what is this? So compare just this shaded portion of the path here. So this is some multiple of mu, right? So what is this shaded portion? Let me just draw an arrow here until this point. This portion is some multiple of mu. What multiple? Well, a mu, where a is that rational number, the time stamp. So let's say this happened at t equals a, then this shaded portion is a times mu. Okay, and this thing on the bottom, the length, that guy, the direction is nu, but this endpoint is a nu. So I should say this endpoint is a mu, and this endpoint is a nu. Right? Is this fine so far? Now, when I perform this operation, what's happened? It's lowered this endpoint. Okay, in other words, a mu minus a nu is alpha I. Right? This is what must have happened when I applied an Fi. That mu became some other direction nu, such that the differences in their endpoints works out to be alpha I. Now what does this mean? This says that a times mu minus nu is alpha I. Okay. In other words, mu minus nu is some positive rational multiple of alpha I. So mu minus nu is therefore it's some 1 by a times alpha I. So this is some, let's say this is some positive rational multiple of alpha I. Okay, this is fine. So this is what must happen when the direction changes. They must differ by some positive rational multiple. But now there's a little bit more we can say. Mu and nu are also Weil conjugates of the same. Mu and nu, remember, we're both Weil conjugates of the same lambda. They are in the same orbit. Now all fellows in this orbit will all differ from each other always by an element of the root lattice. Okay, so this is another fact, if you wish, that this means that mu and nu, so this fact will sort of keep recurring many times. Mu minus nu is actually in the root lattice. In other words, it's in the integer span of the roots. Okay, so all Weil conjugates are mutually congruent to each other modulo the root lattice. So in particular, mu minus nu is some positive rational multiple of alpha I. It just means that in fact this must be an integral multiple. We know already that it's an integral multiple of integral linear combination of the alpha i's. So here it's a positive rational multiple of a single alpha I, means that multiple must in fact be an integer. Okay, this is telling you that it's an integer. So in other words, using this fact we conclude that mu minus nu is actually a positive integral multiple of that single alpha I. Okay, in particular it means mu minus nu is in Q plus. Okay, so in some sense this is really the genesis of this definition of this partial order. So if you remember what we were trying to do yesterday, trying to define a partial order, what did we require? We said nu is greater than or equal to mu, means that they differ by an element. The thing on top, this minus this is an element of Q plus. Okay, and they are both Weil conjugates. They differ by a reflection. So you can already see all those facts here. Mu and nu. So what do we know about these two guys, mu and nu? So finally here's the conclusion, that this two segment path has two directions, nu and mu, with the following properties. nu is nu and mu differ by reflection. So this is Si mu. Here it's just a simple reflection. Mu minus nu, the second guy minus the first guy, is in fact an element of Q plus. Okay. So what this says is, these two things imply in particular that this nu is more than nu in that partial order we talked about last time. So nu beats mu with respect to that partial order. Okay. So what this says is, so if you think in terms of applying FIs to paths and when you generate newer paths from an existing path, what happens is the direction which changes always has this property that the first direction you move along, that guy is always greater than or equal to the second direction. Okay, so there is some linear ordering on these directions. So I sort of remember last time I was saying these nu i's cannot all be arbitrary elements of W lambda. So here's sort of one condition which is suggested by this heuristics, that they must be in decreasing order. Nu 1 must be bigger than or equal to nu 2, greater than or equal to nu 3, etc., etc. Okay, so there is this decreasing condition on the directions, which we sort of see from here. So that we will put into this definition. So instead of talking about paths of class lambda, let me call these rational paths of class lambda. So rational paths of class lambda. So what are these? So this is yet another class. So let's number these guys. This is the first set. This is a set we are trying to understand. This is a much bigger set that we constructed. Here is now a set which is somewhat smaller than this. So rational paths are also paths. Okay, with one constraint being that, so this is all paths pi, paths, so pi paths here, such that these directions, so I'll just think of pi as this path here. So pi like this, with the property that there's a decreasing condition on the directions. So this is dot 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 nu r. Okay, so the directions form a decreasing chain. So and in fact, I mean, I don't need to put equality. If two directions are equal, I'll just merge those two bits together, think of it as a single direction. So I might as well just put strict inequality, nu 1 greater than nu 2 greater than nu r. I mean, this is just Littelmann's, yeah, exactly. Yeah, I mean, clearly it doesn't, it doesn't mean anything here. Yeah, so I'm just, by the way, all of this, like I said yesterday, is from Littelmann's analysis paper, and this terminology is, so I mean, in addition to all his notation, I'm sort of introducing some new terminology here and there. So he doesn't talk about paths of class lambda. So this is just something I'm using as an auxiliary here. So he defines these. Okay, so what do we know now? Why did we impose this constraint? It seems, our heuristics there at least seems to suggest that B lambda is in fact contained in this set itself, not just in this bigger set of paths, but rather in the constrained set of rational paths. Okay, the directions that you travel along must be decreasing. What? Right. No, in a sense, I guess Shamik's question is, where is that inequality? I mean, you're imposing a linear order on, that's not even there somewhere. The fact that the AIs are rational, for example, right? Okay. Okay, so there is still this data of the AIs, by the way. So the path is the directions as well as the timestamps, right? So this AIs are all still there. So this last timestamp here is t equals AR, which is 1. So 1. So I'll call this 1 as AR. Okay. Now let's look for more conditions. Turns out that this is still too big a set. Okay. We are looking at, we are trying to find out what are all the conditions you need to get exactly B lambda to carve it out. We have gotten one condition. Now it turns out there are more conditions. So let's look for more constraints. So if a path belongs to B lambda, what else must it satisfy? Okay. So here, by the way, like I said, it's mostly heuristic. I haven't really proved that it's contained. At the moment, it's only suggestive. But this one is more rigorous. So if pi is in B lambda, so here's the first observation. What does it mean to say it comes from B lambda? It's a string of f's on the path pi lambda. Okay. Now any string of f's will lower, each f will lower the endpoint by the appropriate amount. So this is, if you wish, minus alpha I1 minus alpha I2 and so on. Okay. The endpoint of this path will therefore look like lambda minus some element of q plus. Okay. This is a sum, if you wish, of some bunch of simple roots. So in other words, this endpoint is of the form lambda minus some element, in other words, lambda minus pi 1 must be in q plus. Okay, must be an integral combination of the simple roots. Okay. Now let's see what this condition implies. Okay, to the one segment and two segment paths that we have considered, at least for now. So if your path is just a one segment path, for example, something like this. So let's just say I have a one segment path, say, so let's say pi is a one segment path, which means it ends at some while conjugate mu of w lambda. Then this condition here, lambda minus pi 1 is in q plus, is automatically satisfied. Okay. So if I take any element, any while conjugate, then observe that lambda minus any while conjugate of lambda is automatically in q plus. Okay. So this is a fact, if you wish. Fact, because lambda is a dominant integral weight. So here's a fact. Lambda is a dominant integral weight, then lambda minus mu is in q plus for all while conjugates mu of lambda. Okay, just a easy fact about while groups and so on. So what this means is that if your path is just a one segment path, then this additional constraint that we impose is not a constraint at all. This is automatically satisfied. Okay, so that doesn't give you anything for one segment, guys, but two segment paths again. So let's look for two segment paths and impose this constraint. So suppose I have a two segment path which comes from B lambda. So let's say pi, suppose pi is a two segment path in B lambda, then what can we say about pi? Okay. So what's a two segment path? It has two directions. It has one timestamp, t equals a. So this is t equals 1. So the two directions nu and mu, and we've just said let's look for, the condition seems to be that nu must be greater than equal to mu. So at the moment, all of this, think of it as somewhat heuristic. So nu is strictly greater than mu. So let me assume this as well. Okay. So nu is greater than mu. Now let's try to impose this condition that lambda minus pi 1 is in q plus. Okay. So if this came from B lambda, let's compute lambda minus pi 1. So this is lambda minus, so what is pi of 1? What's the endpoint of this path? It travels along this direction for this much time. So the endpoint is a times nu and then it travels along mu for 1 minus a time. So 1 minus a times, okay, which is lambda minus mu plus a times mu minus mu. Is this fine? Yeah, I am always only talking about directions, yes. Mu and nu are some wild conjugates of lambda. So that's only the, so when I say arrow and put a nu or mu next to it, it just means direction. Huh. That's if you apply only a single Fi you're thinking, but maybe subsequent Fis might do something to it, right? So we don't know for sure what happens when you apply another Fi. So maybe that impacts the mu in some sense. Okay, so I computed lambda minus pi 1 and found that it is this, lambda minus mu plus a times mu minus nu, and what we know is this must be in Q plus. Okay, so now observe, so what does it tell us? First thing, lambda minus mu, as we just said, that's already in Q plus. Okay, so lambda minus mu is in Q plus, in particular it's in Q. So actually Q is all I care about at this point. So this is an element of the root lattice. Okay, the right hand side, the answer is an element of the root lattice. It's in Q. In particular, that means that this term must be an element of the root lattice. Okay, so this guy, so we can ignore the Q plus for the moment. So this is in Q is enough. No, that's what. So that's what Chamak is also asking. See, I'm only looking. That is only if you applied a single Fi, then it looked like that. Yeah. Huh? Yes. No, no. Why am I applying Fi power m? I'm only applying. I could be applying a single Fi. No. See, that is. I'm not doing one segment paths anymore. I'm allowing anything. But my final answer should look like a two segment path. So, I mean, I'm just, so in some sense I would say, see, like I said, it was a heuristic, so don't take it too seriously. Broadly speaking, if you apply Fis, let's say the Fi impacted the second part of the path, then that mu, that, I mean, it could have been lambda to start with, but that will again become some other Fj lambda, I mean Sj lambda at some point. So it's conceivable that it will change, it may not remain lambda the whole time. Right? And if you actually work out a few examples, you will see that it won't. So for example, the thing that was done in the tutorial for the adjoint representation, you would have seen a two segment path in which the two directions are not lambda, they are both, you know, some other conjugates of lambda. Okay. Correct. There are many other ways in which two segmented paths can arise. Exactly. Correct. So I can have a three segmented path in which one of the segments now gets reflected so as to coincide with the preceding direction, and then it merges into a bigger two segment path. So things like that, there are many ways of getting two segment paths. So at the moment, you know, just one heuristic which tells you that if you start with, say, the path lambda, then at least something is happening. Yeah. Okay. So now let's see what what condition this imposes. See, this is an element of Q plus, so I mean, in particular, it's an element of Q. Okay, this is already an element of Q plus, therefore an element of Q. Therefore, this bit must also belong to Q. Okay, so conclusion, this belongs to Q. Fine. So now observe, this is an additional condition. So this says that A times mu minus nu is actually an element of Q, and again, remember that since this condition holds that nu is greater than mu, what does this mean? This means that by definition mu minus nu must be, it's an element of Q plus already. The difference is in Q plus. Okay, so therefore A is a rational number, it's a positive rational. So what I'm saying is, here is an element of Q plus. When I multiply it by this rational number, the answer must continue to be in Q plus. If you take an element from q plus, which is an integer combination of some alpha i's, and you multiply it by a rational number, all the coefficients of the alpha i's have now been multiplied by an alpha by that rational number a. Okay, the coefficients are all now rationals in general, but you demand the stronger condition that those coefficients must continue to be integral. Okay, so this is still in q plus. So that's the conclusion. So this is an additional condition. A times mu minus nu is an element of q plus. Fine. So this is one more thing that we are deducing from our analysis of two segment paths. So let's put that in as part of the, let's make another set. So this condition I'll call the integrality condition at A, or maybe no. Let's just refine it right away. So this condition here, we'll call this integrality condition. So this is the integrality condition. So what do I mean by the integrality condition? So a triple, there are three pieces of information here: nu, mu, and a rational number a. Okay, so this triple nu mu a is said to satisfy the integrality condition. So satisfies the integrality condition, I see, if the following happens. So what are the elements of the triple? So here a triple nu mu a where nu, mu are some Weil conjugates of lambda, nu is bigger than mu in that partial order, and a is some rational number between 0 and 1. I guess you can also put, no harm putting 0 and 1 there. Such a triple satisfies, I see, the integrality condition if the following happens: if not just mu minus nu, not just that belongs to q plus, but a times mu minus nu belongs to q plus. Okay, so this is something more. It tells you something that happens at that rational number a. That rational times this difference is there. Okay, so that's called the integrality condition for that triple. So what, again, what this suggests is that if you had paths in B lambda, then, or at least if you had two segment paths, then they must satisfy the integrality condition at each time stamp. Okay, so observe, a multi-segmented path is sort of like locally at each time stamp, it's like a two-segmented path. So what you have is, if I have a multi-segment path like this, at each time stamp I have two directions, one incoming direction and one outgoing direction. Right? So at any time stamp t equals ai, this is what the path looks like. There's some new I minus 1 direction, new I direction that comes in, and then a new I plus 1 direction which goes out. Right? This is how the path looks, no matter what happens there. Okay, so this sort of suggests that at each t equals ai, you need to impose the integrality condition. Okay, now it turns out that even that's not enough. Okay, so I could actually write out one more class of paths here, rational paths with IC, which would mean all paths which are rational, further which satisfy the integrality condition at each time stamp. Okay, so that will be rational paths with IC. Turns out even that's not enough. You need something even more stringent. Okay, so we'll call that the strong integrality condition. So in addition to this, I need to impose a stronger version of this. So this is strong integrality. Okay, and so let me explain what the strengthening is. So strong integrality says the following. So a triple as above, nu mu a satisfies strong integrality if the following happens. So let me write out the definition here. So what does integrality say? I have nu and mu, which are, so if you remember that diagram, so here's nu and here's mu. So imagine all this is in that diagram, that hexagonal diagram that I draw. Or more generally, we might be in some other. So this is a diagram of W lambda with that partial order. So I'm drawing the poset W lambda, okay, partially ordered set. So there's some partial order here, and nu and mu are like this, right? Nu is bigger than mu. Now, what does nu bigger than mu mean? The full definition, it says that I should be able to find a sequence from nu to mu such that each guy it differs by a reflection and each difference is in positive q plus, etc., etc. Now, the strong integrality says the following. So, what does this weak integrality say? It says that I take just the difference between these two ends and multiply it by a, it should be in q plus. Strong integrality says you should be able to join these two guys by a saturated chain, by which we mean you should be able to find a sequence in this partially ordered set, okay, such that each successive thing is just distance 1. So, recall this notion of distance we talked about last time. So, I should be able to reach mu from nu through a sequence of distance 1 moves. Okay. What does that mean? Each thing here, they differ by a reflection. This minus this is in the positive lattice, and there is no longer chain which will take me from here to here. This is sort of the only chain there is. Distance 1 means that's the maximum length of a chain that can get you from here to there. Okay. So, these are sort of successive neighbors. I can't do anything. I can't reach the same point by some longer route. Okay, so I have to find distance, a saturated chain or distance 1 sequence like this. So, let's call this nu 1, nu 2, nu 3 till nu r. Let's call this nu 0. So, strong integrality if there exists a sequence nu equals nu 0 greater than nu 1 greater than equals mu in this partially ordered set, which means such that nu i's are all in W lambda for all I. The distance between each successive pair is 1. Okay. And that integrality condition A times mu minus nu is satisfied for each successive pair. Okay. Huh. Yes. One is no. The partial order includes in terms of q plus, you mean just in terms of, no, I'm never using that partial order. I'm never using that. Meaning I'm never saying if lambda minus mu is in q plus, then lambda greater than or equal to mu. I mean, that's the partial order we use when we talk about weights and so on. But I've sort of not used it specifically because it will confuse with this other partial order. This sort of goes in the opposite direction. Yeah, absolutely. So here for me it always means nu greater than mu means they are, they also differ by reflections, right? I mean, I should be able to reach one from the other by reflections. That's another condition here. And then this portion of the thing is the opposite of the other convention. It's mu minus nu should be in q plus. So yes, in terms of reflections and this difference in q plus, yes. So if I want to use that partial order, I'll always say mu minus nu in q plus. I won't write a greater than symbol there. Yes. Yeah.
But they are not equivalent.
No, not all. I mean, there's a one-way implication. Of course, if this is true, then mu is less than nu in that partial order, because that partial order is only defined by this condition. This is all you need for that partial order. Sorry, what? If they are conjugates of the same lambda? Is it, does it mean they are linked by a sequence of reflections, you mean? So this is like asking it for the Breuerorder, right? Does the Breuerorder have that property? Just being less than or equal to, will it imply that it is greater than in the Breuerorder? Right? You can take lambda to be a rho, for example, or some regular dominant weight. Then it's like asking whether the Breuerorder is just determined by whether W lambda, W rho minus whatever, tau rho minus sigma rho is in Q plus. I doubt if that's true. Right? I'm not sure.
Then you wouldn't need such a complicated emission.
Correct, exactly. Yeah. Okay. So is this thing about strong integrality clear? It's a slightly involved definition, but what it says is rather than just requiring that the two endpoint differences, just taking the difference between these two guys and multiplying by A, demanding that that should live in the root lattice. That's the weak integrality. Strong integrality says you should be able to find a chain, a maximal sort of a saturated chain which gets you from here to there, such that each pair is weak integral. I mean, that integrality holds for every pair here. What is related? No, because these are all while conjugates of the same lambda. See, they're all while, you are traversing the while orbit of lambda. This string is not that. Is that what you're asking? Whether this string is related? No, not really. This string is, you are traversing the while orbit of lambda. Right? These are all elements in the while orbit. So it's, yeah, it's something else. Huh? No. So yeah, you're right. So I mean, like you said, can it be somehow motivated by heuristics? Some examples where, good question actually, I don't know. So in fact, a related question is that, what if you didn't impose this strong integrality? So like I was saying, rational paths with integrality condition, rational IC. Now we are saying rational with strong IC. That's sort of going to be the eventual set where we'll be interested in. But why not just consider rational paths with IC? Does it have nice properties? Maybe that's a research question, I think. Like you just impose, you will get a larger collection of paths. Okay, but let me define this collection. So this is called, this is rational paths with strong IC, strong integrality condition, will mean, by that I will mean the collection of all paths, all rational paths. So this is the collection of all rational paths of class lambda, which means things like this. So rational paths just mean you have a decreasing, the traversal directions decrease. You have some timestamps. Strong integrality means that when you have two segment paths, that A and these two, the incoming and the outgoing directions and the timestamp, the three of them have to be, have to satisfy this integrality condition. So this sort of strong integrality condition. The incoming direction and the outgoing direction should be connectable through this sequence of distance 1 things, such that every pair of them satisfies integrality. Okay, so pi in rational paths, and now here I demand this for every timestamp, not just for, it's a multi-segmented path in general. So now I say it's all rational paths such that each triple, incoming direction, outgoing direction, timestamp, each of these triples satisfies the strong integrality condition. Okay. So this is the collection of paths that we will finally be interested in. So sort of a remark about notation and so on. I've sort of changed the terminology of many of these things. So this strong integrality condition, having a chain like this. So a chain like this is what Littelmann will call an A chain. Okay, this is called an A chain connecting nu and mu. Okay, and so this condition would be worded as it's all rational paths such that for every at each AI there exists an AI chain connecting the incoming and the outgoing directions. Okay, and this is the collection of paths that will be important for us, and this has another name. It's called the set of all Lakshmibai Seshadri paths of shape lambda or class lambda. So this is called, so L and S are Lakshmibai and Seshadri. Okay, and so let me state the main facts about these, and in a sense it will be what we set out to do, that this class B lambda is exactly captured by these conditions. You need to have a rational path, which means decreasing directions, such that there is a strong integrality which takes place at each timestamp. Theorem which you will find in Littelmann's paper as corollaries 2 and 3. So this theorem is due to Littelmann. So let me state the various facts about this. Number one, the set of so what is the setting? Let G be well, for us a finite dimensional simple Lie algebra for now, but all this works in complete generality. You can actually take what's called a symmetrizable Kac-Moody algebra, which is an example of this is the affine algebras that Venkatesh is talking about, for example. So G be this, and let lambda be a dominant integral weight of G. Theorem says the set of all Lakshmibai Seshadri paths of class lambda is closed under the action of the EIs and the FIs. Okay, this is the definition. The claim is that this is closed under the action of the EIs and the FIs. And of course, I mean, there's just one silly thing to take care of. When you apply EIs and FIs, sometimes it's not defined. So you say EI acting on a path is 0, right? So I will have, instead of that, I'll have LS lambda union 0 is closed under EIs and FIs. The root operators for all I. EIFI on 0 is just defined to be 0. Okay, so this is the first theorem. Statement 2 says that every pi for every pi in LS lambda, the number, the minimum value. So if you remember mi pi, which I had defined as the minimum value that this h function takes. If I take any Lakshmibai Seshadri path, it has this additional property that when you draw the function hi for it, the minimum value is always an integer. Okay, the minimum is always attained at an integer. So this is also sometimes called the integrality property. So there are too many integrality properties in this business. So the minimum is an integer. Now fact 3 says let pi be a Lakshmi-Seshadri path of class lambda, then pi is in LS pi, then EI pi is 0 for all I. It's killed by all the EIs if and only if it's the original straight line path, if pi is pi lambda. So by the way, notice that the definition of the Lakshmi-Seshadri paths, I mean by this definition, all the single segmented paths are automatically in LS or in LS lambda. Okay. The condition for LS is really, it kicks in only when you have two segments really. Okay. When I have two segments, then there is that time stamp at which a transition occurs between the incoming and outgoing directions, and there you need to impose the integrality. Right? This SIC only kicks in when I have some AI which is neither 0 or 1. Right? If the only there are no transitions really. You start at 0, keep going the same direction till you reach 1, then this condition doesn't even kick in. It's trivially true. It's vacuously true. So therefore, all single segmented paths are automatically LS. Okay. So in particular, the original path is there. The starting straight line path is definitely in LS lambda, and so are all these other paths we looked at, all the ones ending at W lambdas. Okay. Okay. So this is fact 3. Fact 4 says every pi in LS lambda can be written as pi in LS lambda. Means pi can be written expressed as some string of f's for some lowering operators Fij's. Okay. So notice that the last condition was sort of where we began. I mean, that was what we attempted to somehow construct, right? What are all the paths you get when you keep applying f's to your pi lambda? And then we tried to get more and more constraints on such paths. And finally, you arrived at this axiomatic, this definition. You describe a bunch of conditions and you collect together all paths which satisfy that condition. So of course, in the end, this theorem sort of says that you have gotten exactly what you wanted and nothing more. Okay? Every path here is necessarily of this form. Okay? And it's exactly all paths of that form. That's the other thing. That's what this says. It's closed under EIs and FI. So you take pi lambda belongs here. So you keep applying FIs to it, it'll again belong to the same class. Further, any path in LS lambda is in fact of that form. Right, that will follow from the theorem. The very first condition. So let me make all those remarks. So corollary in our notation is B lambda equals LS lambda. Corollary in our notation is that this set B lambda is exactly the set LS lambda. Okay, why? So let's just see how this would follow. Right. Step 1, LS lambda is contained in B lambda. That's exactly the last statement. It says that any path in LS lambda is of this form. Okay. So by 4 we have one-way containment. We get B contains LS. Okay. Now let's do the other way around. Now observe pi lambda. So we need the following fact. Note that pi lambda belongs to LS lambda by definition. Right? This is the thing I said. Single segment paths, that condition doesn't even kick in. So pi lambda is surely in LS lambda. Now, by property 1, it says that LS is closed under the actions of the EIs and the FIs. So, if I act a string of FIs, then of course it's going to be in LS. So, therefore, any string of Fs acting on pi lambda, the answer will continue to be in LS by property 1. Okay. Therefore, B is contained in LS. Right? This collection of all such guys is what we call B. Therefore, B is contained in LS. Is that fine? In not playing a role meaning? Right, every element of B lambda can be gotten just by applying Fs. In that sense, yeah. But they play a role in the sense of if you are somewhere, you want to get to some other points in the crystal graph. So this is really that crystal graph thing that we drew, right? We started out with that pi lambda that kept applying Fis. But of course, when you are somewhere in the crystal and you sort of want to go up further, for example, or to some other points of the crystal, you may want to apply EIs. In fact, we will do it in one of the proofs. If you want to get back to the top, starting with something, you have to apply EIs, for example, because E's and F's are sort of inverses of each other. Okay? So let's, I'm not going to prove one today, but let's see the proofs of the other statements. Okay. Now, let's prove. Let's see which of these is easiest. Let's prove the last statement, starting from the third one. Okay, so let's prove this theorem. Proof of some parts of the theorem at least. Proof of theorem. So let me prove 4. Part 4 of the theorem follows from part 3. Okay, so let's see how 4 follows from 3. So let's prove 4. Okay, we'll use 3 for this. So we'll use 3. So what do we have to prove? Let's assume that this is known, that the only path in LS lambda that's killed by all the EIs is a straight line path itself. Okay, I'm going to assume this fact, and now I'll show that 4 follows. Okay, what does 4 say? That this any pi has this form. Okay, so let's take pi. So let's prove. So to prove 4, let pi be an element of LS. Now, how do I write pi in this manner? One way of doing this is the following. You try to apply ease. Okay. So how do I show it? It can be written as something like this, pi lambda. I sort of apply the ease. So if you remember, ease and f's are inverses of each other. So pi lambda can therefore, if this is true, pi lambda can be obtained as ei1, ei2 till eik acting on pi. Right? I just take each f to the other side. So eik pi, eik minus 1 pi, and so on. So that string of e's acting on pi should give me my pi lambda. Right? That's how I can reach my pi lambda from pi. Okay, so let's do that. So let pi belong to S lambda. So step 1, if all the EIs kill pi, if EI pi is 0 for all I, that means what must pi be? Pi must already be pi lambda, so I am done. Okay, if all the EIs kill it, it's already pi lambda by 3, right? I said I'll use 3. Okay, so this is by 3. Suppose, so if this is not true, that means at least one of the EIs doesn't kill it. Okay, so let me use the EI. So if not, there exists some EI1 at least, such that EI1 pi is a non-zero answer. So let me call that pi 1, which is not 0. Okay, I get pi 1 from here. Okay, now if pi 1 is killed by all the EIs, then pi 1 must be pi lambda. Right, and again I am done because pi 1 is just ei1 pi, so pi can be obtained as fi1 acting on pi 1. Okay. So if pi 1 is killed by all the e's, I am done. If not, there is some e which will act on pi 1 and give me another guy. Correct? So I keep going like this. Okay. Now this process, if it stops at some point, okay, so keep going. So if ei pi 1 is 0 for all I, pi 1 must be pi lambda, and again you're done. Else find ei2, which will give me another path, another non-zero path. Go on. Okay. If the process stops, once the process stops, you're done. Whenever it stops, wherever it stops, that last path must be pi lambda according to 3. Okay. And now you just retrace your path. Instead of applying that string of e's, you apply the corresponding string of f's. Yes. Yeah, there are only finitely many. For some finitely many fj's, yeah. I mean, what does it mean to apply an infinitely many? I don't know. I'm only applying some finitely many operators. Right? So is this fine so far? The basic idea is clear, right? The only thing we need to figure out is why does it stop? Why does this process not go on indefinitely? How do you know it stops somewhere? What? Okay, excellent. So each time I apply this operator, there's something, something is becoming smaller. Okay? So there is something that's happening, and that's something that we used in order to sort of motivate the definition of LS and so on. So which is just the integrality condition, not even the strong integrality. So recall from whatever we did, the following fact, that if I started out with something in LS lambda, okay, in fact, not even LS, just a rational path with integrality condition, right? Just rational and IC, such a path automatically has the following property, that lambda minus pi 1 must be in Q plus. This is how we motivated the integrality property, in fact, right? The integrality condition. Lambda minus pi 1 is automatically in Q plus whenever pi is in LS. How? You just do that calculation again. You have to do it for every timestamp. I only did it assuming 2 segments, but the proof is the same. Okay? So check this from the definition of LS. Now, because of this, what it means is that this is some integral linear combination of, so what is Q plus? Q plus is just some integral combination of the simple roots. Okay? So we can measure. So what is going to happen in the next step? So let's call this something. So let's write. So if you look at the endpoint lambda minus pi 1, it can therefore be written as some linear combination of the simple roots with all these ci's being non-negative integers. We can use the ci's to measure the smallness of the process. So let's call it height or depth or whatever. So let's call the depth of pi to be the sum of the ci's. This is something we'll use to measure. This is something that will get smaller as we progress through this process. Okay? So observe that the depth of this path is always a non-negative integer. Okay? Now what happens when you apply ei to pi? So that's the analysis we need to make. So observe, if you apply ei to pi, then the new path has endpoint which has become 1 larger, right? I mean, you have added some alpha I to the endpoint. Okay, so once you add an extra alpha I, by the definition of depth, I need to do lambda minus this. So one of the ci's, I mean the ith guy, ci has now become ci minus 1. Because of this, adding this plus 1, if I write lambda minus this, what that amounts to is that ci has become ci minus 1. In other words, the depth of this new path is 1 lower than the depth of the original. Okay? And the depth remains always a positive, a non-negative integer. Right? The depth is always greater than or equal to 0. At every step, you are decreasing the depth by 1. So, of course, this process can't go on forever. The maximum number of steps before which it terminates must be the depth of the original path that you start out with. Is this fine? Okay, so the process ends. So that process ends and you're done. Okay, fine so far. So that's proved 4, assuming 3 is true. Okay, so 4 is done provided we prove 3. Okay, now let's prove 3 assuming 2. So I'm going to assume that 2 is true, that these paths all have integral minimum values. MI's are all integers. So let's look at statement 3 that we need to prove. It says that ei pi is 0 for all I if and only if pi is equal to pi lambda. Okay, so one way is obvious. If pi is equal to pi lambda, all the ei's are 0. I mean, we have in fact done this. We actually did this when we computed, right? Yesterday when we did that crystal graph, you started with the straight line path to 2 epsilon 1 plus epsilon 2. It was necessarily killed by all the ei's because the minimum value was a 0 in this case, right? Because lambda is dominant. So this implication is obvious. So let's prove the other implication. So we need to prove this one. So let's take a pi in ls lambda, and it's killed by all the ei's. Now what does being killed by all the ei's mean? Mi pi is greater than, this is when a path is killed, right, by the ei's, when the minimum value it attains is strictly bigger than minus 1. Okay, but now I'm going to assume 2. Okay, so I'll prove 3, so let's assume 2. So by 2, what do I know? I know that these minima are actually integers. Okay, and the minimum is greater than minus 1, therefore it's actually 0 or more. Right? So all the minima are 0 or more. Is this fine? Okay. Now let's show that this must be a straight line path. Okay. This property that all the minima are 0 or more forces this to be a straight line path. Okay. Why? Because what is your path pi in ls lambda look like? It's a multi-segmented path in general. So let's say this is your path pi. So what does it do? First direction nu1 until time a1, nu2, nu3 and so on. Nu1 greater than nu2 greater than nu3, right? So this is just a rational path, nu1 greater than nu2 greater than nu3, blah blah blah. Now what do I know? That this path, its mi pi is greater than or equal to 0 for all. This means that the path always stays above the hi, so this is true. If I draw the hi graph, that hi will always stay above the x-axis, right? The pi t of alpha I check is greater than or equal to 0 for all times t. Okay, so let's compute what is, what happens to the values of pi t alpha I check when I traverse the first segment of my path. Okay, so here's my path. Let me compute the value at t equals a1. Okay, so let's calculate it at t equals a1, that's already enough. So let's just calculate at t equals a1. What's the value of pi at a1 evaluated at alpha I check? So at t equals a1, the path would have reached the point a1 times nu1, right? So this path would have, this is where it is. It's at a1 times nu1, and I have to evaluate that on alpha I check. Okay, and this has to be greater than or equal to 0. That's true for all I. In other words, since a1 is a positive rational number, it means that this nu1 of alpha I check is positive for all I. Okay, so this means that nu1 of alpha I check is greater than or equal to 0 for all I. Okay, now this property says that if you go back and look at the definition of what P plus was, the dominant lattice and so on, this actually means that nu1 is actually dominant. Right? This is what dominance means. Right? It's already integral, but this means it's actually dominant. It's also greater than or equal to 0 for all I. But remember, all these nu's are Weil conjugates of a particular lambda, right? They're all Weil conjugates of the chosen dominant weight lambda. Okay, it's in the Weil orbit of lambda, and what we are saying is nu1 is a dominant element of the while orbit of lambda. Okay. Now the while orbit of lambda contains only one dominant element, which is lambda itself. All the other guys are non-dominant. Okay. So this property says, therefore, so I mean now I'm going to use some facts about the orbits of lambda. W lambda contains a unique dominant element okay. So W lambda intersection P plus is just lambda, contains a unique dominant element. And further, the second fact, which was clear from the diagram we drew, when you take the partial order, so W lambda with that partial order, this has a unique minimum element, which is lambda itself. Okay. This partial order has lambda as its unique minimum element. So the minimum element of this partially ordered set, W lambda this, is lambda itself. Okay. So it is the smallest element. It's smaller than all the other elements in its W orbit with respect to that partial order. Okay. Now what does that give us? If you just apply it to nu1, so conclusion from our proof is that nu1 should therefore be lambda, because nu1 is dominant and it's an element of the while orbit. So I've used fact 1. Okay. By fact 1 means that nu1 has to be lambda, okay, the unique dominant element of its while orbit. Now what does fact 2 tell you? What does fact 2 give you? So I have concluded something about the first segment, that this must be traveling along the direction lambda. Now what can you conclude about nu2 now? Right? So observe that this must be true, that this direction is bigger than this, but lambda is the minimum guy in its orbit, right? So there cannot be a nu2. There is nothing smaller than lambda. Lambda is the smallest. Fact 2 means there is no nu2, nu3 and so on. In other words, it's a single segment path. In other words, this path pi must just look like the single segmented path which ends at lambda. Okay. So in fact, if you see what we have proved a little bit more, that the initial direction, if you take an LS path of shape lambda, you can never have the first segment be lambda. The initial segment can never be lambda. It's always something else. Because the initial segment is lambda, all subsequent segments have to be lambda as well. I mean, there cannot be subsequent segments satisfying this inequality. It can possibly be the last. That's the only possible place it can be. Yeah. Okay. So is this okay? So we have to sort of keep using facts about the while orbit and so on and so forth. So okay. So we have proved 3 now, that this is the unique path which satisfies this property, assuming 2, right? So now in some sense we have to prove 1 and 2. So like I said, I'm not going to prove 1, but I'll give you some idea about 2 at least. So just a remark about all of this. So notice right here that this is already starting to mirror the representation theory in some sense. So what Ravinder's been talking about, having this highest weight vector and so on. So if you notice that it's exactly this, right? This path pi lambda, the unique path. So what this is pi lambda is a unique path which satisfies this property. It's annihilated by all the EIs. So at the level of representations, it's like saying you have a highest weight vector which is killed by all the upper triangular matrices, right? And in some sense, that's a unique dominant weight vector. So that's really like this. So pi lambda plays the role of that highest weight vector. And again, even in the representation theory, if you have that vector v, the irreducible representation can be described as follows. All vectors are obtained as the span of, just like the EIs, you have FIs, which are these negative, the lower triangular matrices. You can act by the lower triangular matrices successively on the highest weight vector, and that will generate all vectors in your vector space, in your irreducible representation. Okay, so successive applications of the Fs or in the analog of the f's in the representation theory, that will generate the entire representation. Okay, so you can think of these as some sort of combinatorial shadows of those facts. Yeah. Okay. So now let's try and prove 2, or like I said, I'll give you some idea about 2. So this so the fact that this thing is a minimum, it attains an integral minimum. It's a very important fact in some sense. And it sort of comes from, again analyzing 2-segment paths at some level. So I'm now going to try and prove 2, some idea of the proof at least. So what's the, when we have a minimum, let's say a minimum is attained at some point. So the minimum will always be attained at some time stamp, right? I mean at a transition point when one direction ends and another direction starts. No, not really. See, there is no action of a Lie algebra on it. It's at the moment, if you think of LS lambda, it's only a set, right? It's not even a vector space. I'm just defining it as a set consisting of these elements. Right. So that's why we sort of sometimes use the word combinatorial shadow, in the sense that it's a set on which you have some operators EA and FI which behave which remind you of what the actual representations do. And I mean, there is the character as well. That's the eventual part of the story. You can calculate the character of this set. It will turn out to be the character of the representation. Yeah. So Raghavan will probably talk about all that tomorrow. So coming back to my MI, so I have a path. So maybe I have many segments in the path, but so this is my path pi. There is a certain point at which the minimum is attained. Okay. So that, let's say this is the timestamp. This is nu I, this is nu I plus 1, this is t equals ai. So in some sense it's enough to look at 2-segmented paths, so let's not put i's here as well. So let me imagine it's a 2-segmented path. I have a new incoming direction, outgoing direction, timestamp. Okay, just a 2-segmented path, and suppose the minimum is attained there. So let's say that the minimum value of hi pi, so this is what pi looks like, the path, is attained at that point A. Okay, so the minimum is attained there. So what does it mean if I draw the graph of hi? So this is my hi, sorry, this is t and this is hi pi of t. So the graph will look like this. So in the first segment, so it's a minimum there, so which means that the segment goes down, then it starts going up. So this is what the graph of hit must look like, right? So the minimum is attained there. Now what does that mean? It means that if I look a little to the left, the graph is going downwards, which means that this direction, when I am traversing along nu, so what is this graph? This is just pi t evaluated at alpha I check. So what I conclude that it's going down here and up there. This translates to the following fact, that nu evaluated at alpha I check is negative and mu evaluated at alpha I check is positive. Okay, because if you see what's the first part of the graph, this is here it's just t nu, that's the direction of travel, right? So t nu evaluated at alpha I check must be negative, right? That's why it's going down. And then as I traverse along mu, the value of hi starts increasing. That can only happen if mu of alpha I check is strictly positive. Only then the value will start increasing again, right? So in fact, this is the sort of thing which you probably did yesterday during, when you, with that grid and so on. Every time you hit a certain line and then go down to another line, the value is increasing or decreasing depending on whether you're going towards the larger or smaller values. Okay, so this is for example what's happening. Now there are other configurations where a minimum might have been attained. For example, you can have this and this. So this is still a minimum which is attained at that point. So this means that the incoming direction is negative, the outgoing direction is actually 0. Right? So you can put these two together and say, well, this, so a configuration like this, nu of alpha hx is negative, and mu is either strictly positive or equal to 0. Either of them will lead to a minimum at that point. Similarly, you can have, the flat thing can also be here. So it's either this is one possible configuration, or this. So this means that nu is 0 prior to the thing, and mu is positive. So I mean, we'll put 0 or less than to again take one of these things into account. Okay. So what I mean is, what's all this? Just way of saying there are basically two configurations you have to study. One is when either this happens, that nu of alpha hx is strictly negative, the other guy is greater than or equal to 0, or you can look at the other case where this is less than or equal to 0 and that is greater than 0. Okay. Now in both these situations, so there is this general lemma or a statement concerning Bruch order, which in which these configurations keep appearing. So let me just state the lemma in both cases. So I won't prove the lemma. So the lemma is the following. It says if this is true, so if I have mu a satisfies strong integrality, has the strong integrality property, satisfies strong integrality condition, and if say this happens, that nu of alpha hx, so then stated like that, let this be true. Now condition 1, if this situation is true, less than or equal to 0 and greater than 0, then here's what you can do. The thing that is, the strict inequality, no for sure is a strict inequality, that guy can be interchanged so when you have this triple, you can form another triple which also has the strong integrality condition. How do you do it? You just, this is the surely positive guy, you can make that an SI. Similarly, if the other set of conditions is true, if nu of alpha hx is negative, mu is greater than or equal to 0, then what you can certainly say is that you can apply SI to nu and it will continue to have the strong integrality condition. Okay. So I mean, the reason I state this lemma is this sometimes what's called the diamond lemma in the Bruch order. So this is somehow the heart of the whole thing. This is really what makes everything work in this whole process, that you can tweak exactly one of the two directions, either the initial or the final direction, and still continue to have this strong integrality be true. Okay. So now using the lemma, so let me just assume this lemma for a moment and now just see what it implies. So the lemma says that, so this already satisfies strong integrality. So because the original satisfies strong integrality, we conclude that it satisfies weak integrality, which in particular means this, that a times this difference must be in Q plus, right? That's because strong in particular means weak. And now look at these two guys, either this is true or this is true, right? One of these two is certainly going to be true if a minimum is being attained, because as we said, minimum, these are the only configurations, either it's like this or it's like this or it's like that. There are only three possibilities for how a minimum can be attained there. And I mean, there's some redundancy here, but doesn't quite matter. So suppose this property is true, that I can interchange mu by SI mu, or maybe the second one is slightly easier. If I have this property that SI nu mu A is integral, satisfies integrality property, from 2 I can conclude that this is true, that again it satisfies weak integrality, that this difference into A is again an element of Q. Okay. So now if both of these, I know now that both these are true, so their difference must be in Q plus, must be in Q at least. So this means that their difference, which is A times nu minus SI nu, must be in Q. Okay. And that difference is in fact exactly the minimum value. So if you compute what this difference is, this is exactly A times nu of alpha I check, I mean the minimum value times alpha I. So this is in Q. That in particular means that this minimum value, which is here, must be an integer. So this is just the minimum times alpha I. Okay, so this is in Q, so the minimum is an integer. Okay, so I know this is sort of very quick in some sense. So my point about this is not so much the whole details of this, but when you eventually read Littelmann's paper, the key point to note is that this is a recurring theme. This sort of lemma occurs all over the place in this business. So you should keep an eye out for that. That how do you tweak exactly one of the two directions? Under what conditions can you do that? Okay, so that's sort of the main ingredient. And having done that, the rest is just a consequence of just this weak integrality. That there are two combinations, both of which give you integral elements of the root lattice. So the difference also gives you an element of the root lattice, but it's somehow interesting, sort of miraculous that the difference is exactly the minimum value. It's the value at the point A. Okay, so just sort of something to help you read Littelmann at some point. Okay, I'll stop here. Does the lemma hold for IC? I see. No, I don't see actually. That's again a good question. That will have some bearing on this other question that we're asking, right? If we just relax the thing, instead of LS, define this larger class, yeah, will it work? So somehow, all the proofs involve going from nu to mu by sequence of length 1 transformations. That length 1 is somehow very important. The fact that you can do that, because then you try to apply. So the way it works, you try and apply an SI to show strong integrality. What do you need to show? You need to show that if you have a sequence, a chain connecting nu and mu, you should be able to find a chain connecting SI nu and mu. The way it's done is you just apply SI to the chain on top. Right? You already have a chain connecting nu and mu. You start applying SIs to it. What will happen is you keep applying SI, you will keep getting different. They will all be distinct. At some point, when you apply an SI, that element of the chain will coincide with its successor in the chain. So then there will sort of be a collapse. So until that point, you apply SIs. Beyond that point, you keep the chain unchanged. So this is the usual structure of the argument. You start applying SIs, the first half of the chain will all suffer an SI, the rest will remain as it is. And then there is a collapse in the middle, which ensures that this is also an A chain, that it satisfies a strong integrality. So all this somehow uses that, being able to go with length 1. If you only had the two ends, I don't know what will happen. It's certainly worth looking into. Okay, stop.